So let's do another elastic collision. So in this case, we're going to start with a big things moving to hit a small thing. So this would be like an iron nucleus as moving to hit a carbon here. Okay, so iron of atomic weight 56 and carbon with atomic weight of 12. And let's say that the initial velocity of the iron is going to be 1.04 times 10 to the 8th meters per second. So close to a third the speed of light. And so now this would be like a cosmic ray. Primary cosmic rays outside the Earth's atmosphere are very heavy nuclei, often iron nuclei, moving at an appreciable fraction of the speed of light. And so it hits a carbon. So let's say it hits a carbon in an astronaut's DNA. So what happens? Well, so it hits the carbon, repels the carbon, so the carbon goes, knocking forward. And so that means the carbon's moving at some velocity v sub c afterwards, and the iron is going to move at some velocity v fe afterwards. Again, they don't merge. We're not talking about nuclear fusion or anything like that, so they're still separate entities afterwards. Because they do not actually interact other than with the electric force, which is conservative, then initial and final kinetic energies are the same. So this is just like before an elastic collision. All right, so like before, then we'd start off saying the mass of the iron times the initial velocity there equals mass of the iron, velocity of the iron plus mass of the carbon, velocity of the carbon. Well, iron 56 atomic mass units, and then carbon is 12 atomic mass units. So we divide all this out. V sub I equals V sub Fe plus 0.214 V sub C. Now we know we're going to have to solve here for something. So V sub Fe is going to be V sub I minus 0.214 V sub C. And we also know we're going to eventually have to square that. So that's V sub I squared minus 0.428 V sub I V sub C plus 0.0458 V sub C squared. So for the kinetic part, 1/2 mass of the iron times the initial velocity squared equals 1/2 mass of the iron, velocity of the iron squared, plus 1/2 mass of the carbon, velocity of the carbon squared. Okay, and so we got 56 V sub I squared equals 56 V sub Fe squared plus 12 V sub C squared. So it's V sub C. Okay, now, well, that's 56 V sub I squared equals, now it's going to be 56 times what we derived before. So that would be 56 V sub I squared minus 24 V sub I V sub C plus 2.56 V sub C squared plus 12 V sub C squared. So those cancel. We get 0 equals minus 24 V sub I V sub C plus 14.56 V sub C squared. That cancels one of those. And so we do a couple more steps. V sub C is 1.65 V sub I. And so that's going to be 1.71 times 10 to the 8th meters per second. Okay. We know that V sub Fe was equal to V sub I minus 0.214 V sub C. So we plug in those numbers and we get 6.74 times 10 to the 7 meters per second. So we have this great big iron coming in, hits this carbon, which is much smaller. And what happens is that after the collision, the carbon goes tearing off out here, and the iron's still moving. Okay, so the iron hits the carbon so fast that the carbon actually ends up being shot off even faster than the iron was moving, and so it transfers momentum and energy, and so the carbon is really tearing off out here. So remember, the iron was coming in here at 1.04 times 10 to the 8th meters per second, but the carbon left at 1.71 times 10 to the 8th meters per second. And the iron is still moving here at 6.74 times 10 to the 7th meters per second. This is why cosmic rays are so devastating to the human body, is that this big iron comes in, it hits a carbon in your DNA, shoots the carbon out so fast, it can actually go hit something else and then knock it out of position. And the iron is still moving so much, it can go whack another DNA strand. And so that's why cosmic rays are particularly devastating, and they're very difficult to shield against as these things come in. So this is another example of an elastic collision.